So, yes, so what I'm going to do today is just to try to give you an overview of Doherty design for higher frequencies than usual, trying to leverage in the factors that make it different, the important factor, in my view at least, and also trying to suggest a few solutions to the problems. Now, being the only academic today, I try to keep it in a way that it seems practical. All these ideas I give you have been tested on real MMICs that we measure over the years. Interesting thing, I spent most of my career working on Doherty design, and I never done a presentation on these. I didn't. This is the first serious thing I did after the PhD was some integrated Doherty design. I realized I never created one. So it's a new presentation. We might finish in 5 minutes or in 2 hours. I never tested it, so we'll see. We'll see how it goes. Yeah, hopefully is the form. Well, so this is an outline. So just try to understand the applications really. So why? Of course, we use Doherty because we want to improve the average efficiency, but it's not the only consideration when we go to higher frequencies. Just a quick overview of what is actually there, what has been published in terms of Doherty design there, and then a bit deeper into the factors that I happen to come across during the years and some ideas on how to improve these. Well, we all know Doherty design from base stations is really the solution, using gallium nitride or LDMOS transistors, but normally comes together with some very powerful linearizer, mostly digital pre-distortion. And up to around 3 gigahertz, we're talking about 2.6, 2.1, 1.8. We're talking big amplifiers, so maybe 300 watt devices combined, and so for big base stations. But more recently, there's been a lot in development for the 3.5 gigahertz for MIMO systems, TDD type systems, where the power is a bit lower. So we start to see some of the things that happen a lot at higher frequency. For example, a lot of the solutions now that you can buy is a single package Doherty, where they integrate most or all of some part of the matching and combiner, and they also integrate drivers. So it's becoming similar to what happens at high frequency. Well, there are a few interesting frequencies now that people are start talking about. The 7 to 15 gigahertz type of range, centimeter wave, they start calling it. There is already some fixed access going there. Point-to-point has been there for a long time. But there are also the idea of using these frequencies for 5G. Seems to be probably the most feasible solution if you want to have more bandwidth, because the millimeter wave, let's be honest, it seems to be not having a huge success. It's still there though, the 20 gigahertz, it has its problems, but there are other applications than 5G where those bands, they seem to be very interesting. SATCOM is one of them. And again, point-to-point has been there for a long time. Above that, I don't know, Doherty will ever be applicable, maybe, but clearly SATCOM is a big word there, point-to-point links, backhauling in general could be useful for telecom. These are medium, lower power applications, so we're not talking hundreds of watts, we're talking maybe 10 watt output power peak, 20 watt, and very often we're talking on power amplifiers that will be integrated in arrays, larger or smaller arrays, but they are in arrays. And still, we need to meet some quite demanding linearity requirements. So overall, the landscape is quite different. Lower power, of course, we need to integrate them, we have to put them in arrays, but it's quite different to the big base stations that people are used to in Doherty design. So a bit of state of the art. So this is taken from the Hua Wang survey, now is at ZTH. So if you look PA survey, you find that this huge database you can download. Now, if you spend a bit of time on looking for just Doherty amplifiers, you can summarize things, what is happening, between, let's say, above 6 gigahertz and to wherever you can find the Doherty amplifier. And this is done by technology. So if we go and zoom in let's say, sub-ranges, let's say we go from 6 to 18, we have a lot of gallium nitride work being done there. Some of it is our work as well. A bit older work on point-to-point. There's still not much on the 5G new frequencies being published there, so it's still pretty new. And clearly a lot of interest in GaN, because most of the technology, you talk about quarter-micron GaN is capable of doing or giving good performance there. The power levels are, even above 10 watt, so there's some 40 watt example there. You can see frequency range is normally not very wide. There is some example of a bit more frequency band, but nothing particularly. Then some example probably for different applications, lower power. The back-off efficiencies that we find here, they're quite good. We're talking between 30–40%, which is quite good at those frequencies. There has been some exercise of trying the Doherty next band. That was a long time ago. Clearly, there wasn't an application then because even the system, typical system for X band didn't require that. It was more of an academic exercise there. If you go, let's say, in what has been a not frequency range recently for 5G, so with the new radio, there's been quite a lot published there using gallium nitride as well. But then you can start finding gallium arsenide examples there. And there is a lot, of course, in CMOS. So there is, of course, the higher power is dominated by GaN. And also bandwidth starts to become important. So people trying to cover the 5G bandwidth of interest. I think most the publications are about 5G. But there are some exceptions. Down in this band here, which I'm cutting a little bit, is the downlink for a satellite. So there's been some work that I've been involved with the European Space Agency to try Doherty there. While up here, most of the publications, they really talk about 5G new range. If you go higher frequencies, there are examples. Some of them are extremely wideband, using indium phosphide. I don't know what application could be or something like that, but in general, there is a lot of CMOS work. So the power levels, you can see that the scale exchange, it goes down dramatically, but there are works in the V-band, Q-band down there in CMOS for applications like WiGig or application there. I think I don't think there's been a huge appetite there for Doherty in general. CMOS just seems to be a bit more flexible and giving good results there. So there is something going on. There isn't too much. I think it's a nice area where more investigation can be done in terms of Doherty. Probably most of you are familiar with it, but just recall it very briefly what a Doherty amplifier does. Well, it's a combined amplifier with two devices. We can call them amplifiers, we can call them devices. One we call the main one, the auxiliary. Up to a certain power, so let's say a relatively small power, only the main is working, the auxiliary is off. So if you look at what is happening in terms of current and voltage on the main device, the top one, we have that is conducting. So let's say it's in class B, so it's conducting for half of the period. And it has some loading that gives a voltage, right? So you create a voltage. But the auxiliary is not conducting, still has a voltage on it because the two are connected together with a non-isolated combiner. But there's no current. So typically we achieve this by biasing in class C. And then as you increase the power, you arrive to a point where the main is basically at the compression, saturation, clipping, you can call it in many ways. This is an ideal model, so the three things happen all together. But basically, it has achieved the maximum voltage swing it can have. At the point, it will be very efficient, so 78.5% in class B ideal, right? And normally, with a normal amplifier, that's where you would stop if you want a linear response, right? So the Doherty allows you to go a bit further. What happens then is that the auxiliary starts to turn on, so starts to have a current, starts to inject a current into this common node here, and it infers what we call a load modulation on the main. So what happens is that the slope of this curve changes from what we call 2R up there, is changing down to a lower value. That means that we can maintain a constant voltage swing on the drain, even though we are increasing its input current. So we never bring the main into compression. We always keep it there just before compressing. So we lose a bit of efficiency, but it's not dropping dramatically, and at least in principle, we have a perfectly linear behavior. Then you keep pushing until also the auxiliary reaches its maximum current and voltage, and the two devices should have at the end the same current swing, the same voltage swing, give you again basically what is the equivalent of a balanced or a combined device. So you achieve, compared to the first high efficiency point, you achieve 6 dB more of output power. So you have a good range where your efficiency looks very good. It's not only the 6 dB there, you have a bit more, you have probably 7 or 8 dB where the efficiency numbers are quite decent. So this is what the Doherty should be doing. I'm just reminded these because if you're not too familiar, even if you are, there are a few things in these mechanisms that become useful when you start to try to understand what can be wrong, can be going wrong at higher frequency. So what is determining the efficiency and the performance of our Doherty amplifier? Well, first of all, we have ATI devices, right? So you need to start from a good device to get some good performance. And the first question that always comes up is, okay, can a device, a millimeter wave, have the same efficiency in a device at lower frequency? I think the answer is, okay, the deep answer is probably related to the slew rate of your device. I think that's, I don't think it's related to FT, it's more related to the slew rate of the device. But the practical answer is, well, we actually did load pool at some high frequency with some fast device. And the results are pretty good. You can get efficiencies close to the 60. We got more, we got 65 in some other cases. But this is an example. I think this was the ohmic process. So this was a 800 micron device using the gallium silicon process from ohmic. These results are at 20 gigahertz, I think around 20 gigahertz. So we did some load pool, we found the best efficiency point around 60%, some certain output power, some optimum load. So, and these, the same results you can get with any decent gallium nitride, gallium arsenide technology. So the numbers of efficiency don't look bad. The question then is how we start from 60% and then we get an amplifier that only does 20. I think that's more where the problem is. We can use load pool to go and analyze one of the always critical points when you do Doherty design, that is, okay, we have a model from a foundry, or we have a model from the manufacturer. How is the model in class C? So we always have this question, don't we? So we can use load pool, we can do behavioral modeling, S parameters, Cardiff model, things like that, to actually use this experimental data and have a better response or a more accurate response in our simulations. And you see what you expect, right? You start biasing in class C, you lose gain, you lose a bit of power as well. So you have to be a little bit careful in the way you choose your devices when you're trying to combine for a Doherty. Because if you get, the main issue sometimes is overlooked. If your auxiliary amplifier is not providing enough power, you say, okay, it's not providing the right load modulation. What does it mean? It means that the main will go more into compression that you expect. And that is very critical because that compression is a nasty compression. It's clipping into the knee and is normally very difficult to linearize. So dimensioning the auxiliary in the proper way is very important, actually for linearity more than anything else. And linearity is the critical bit here because we don't have the big distortion at these frequencies and at these power levels. It's just too much, too expensive. You can also do harmonic control, and like it very often happens, you will find that looking for an optimum of the harmonics is not very easy and not very practical, because you see the points where the efficiency is really, really spectacular, they are quite resonant if you consider your phase to be related to frequency, and normally is, isn't it? So it's very difficult that you will do a design with confidence that puts you in this region. But more likely, you will try to be in a region where you have a good efficiency and you stay away as possible from the region where the efficiency is actually bad. So we found this, quite repeatedly over the years, over any type of device, and it's still true. So also another question that always comes up is, can we do harmonic control on millimeter waves? So this is 20, second harmonic, so it's 40 gigahertz. Yes, you can. If the devices are probably, one technology node better than the frequency of operation. Of course, if you are near FT, it becomes a bit less change here in the numbers. But you can see here we're getting 10% change, and we can easily get something like 6-7% improvement of efficiency if we stay in a region where the behavior is quite flat and nice, so without risking of falling into this bad efficiency region. So that's if we look just at the device. So the devices, they seem okay. Just be a little bit careful on things like harmonic control, which can be a little bit difficult at millimeter wave. Now let's go more into the circuit design and the Doherty operation itself. Okay, the devices look okay. What else do we need for average efficiency? Well, we need the main to be efficient. The main is the only one active, but the auxiliary is off. So the auxiliary off means no current, which means an open circuit for us. Now, an open circuit for a transistor is not really an open circuit. So when we look at a transistor from the outside, we would like to see an ideal open. Now, you look into the transistor, it's not an ideal open. It has a bit of S22 and S12 that gives you some equivalent S22 if you want. And the other problem is you don't only have the transistor, you also have the matching network you will need when the transistor operates. So this auxiliary will have some matching network, even just to cancel out the capacitance, but very often you also need some impedance transformation. So the loss in the matching network also contributes into a degradation of the magnitude of the gamma out, if you want, that you observe looking into the amplifier, but also to the dispersion. So the more you need to match, so the higher, if you want, group delay of your network, the more you have dispersion, so you get more reactive part. But also the more loss you have, the more you're falling inside the Smith chart. What does it mean? It means that a back-off, instead of having the main delivering all the power to the load, some power will leak into the auxiliary output. And that's a loss of efficiency, which is not new because we have millimeter wave. It's just have a higher weight because losses are normally higher. And also the dispersion is faster because normally we're working at higher Q factor. The transistors, they're more or less the same, right? You have a technology node, the Q factor is more or less constant, but then it really goes up with frequency. So we are 10 times higher frequency than we normally operate. The Q factor will go down and then it will go up accordingly. So it will be this phase of the S22 is changing much quicker over frequency. So it's a bit more difficult to control over frequency. So we lose a bit of more efficiency there. And then there is another aspect which is more related, is always affecting the gamma out if you want, but it's more related to the feedback of the device, which again might have an higher input here, a higher frequency. So when your transistor is off, you don't have a current source here, but you still have the capacitance. So you have a feedback capacitance and you have the input capacitance more or less in parallel with whatever impedance you set as the source impedance of the transistor. And this is a voltage divider. So a voltage divider which is, well, how much is that voltage divider? It all depends how is ZS. Now, we have the good habit of trying to match that input, which means that normally we resonate this CGS, which means it's an open circuit. So very often this voltage divider is not great. We're getting quite a lot of voltage on the gate. Now, this voltage that you get on the gate okay, you are in class C, but some of it might exceed the pinch-off, so you start conducting. And this conduction is in phase with the voltage, so you lose RF power, and you also start seeing some DC being drawn by the auxiliary. The only thing you can do then is, well, there are two things you can do. Mismatch, which is always a good thing to do if you want more linearity, is to mismatch the input. But you lose gain. Or you can bias, you can bias the auxiliary deeper, which normally means that you lose gain, because if it is deeper, it turns on slower, so you also need to decrease the gain of the main to make your gain flat again. So whatever we do, we lose gain. And gain, we will see now, that is not very much available at this frequency, so we have a bit of a problem there. Yeah? So feedback there creates a bit of an issue, and at these frequencies you start feeling a bit more. So how do you see it? Well, you can see it as efficiency. You would like to have the gray curve, but in reality, when you start approaching the high efficiency point, you start seeing a degradation of efficiency. Well, this leads to gain, right? So it's very easy that we design a Doherty then for many reasons, bandwidth, just what the device does. When you start going at these frequencies, it's very easy that you do your design and then you have this number of gain. So if you have that number of gain, normally you need a driver, and the driver has an impact on your DC consumption. So this is, as I say, this was when I started working on this thing. You say, okay, we put a driver there, what can we do? I mean, one solution is to have the driver that is a Doherty itself. That I've seen it done. I haven't seen it done integrated, but it's been done for lower frequencies, PCB type. But then we started thinking, okay, what if you split the driver? So we come up with a way, can we demonstrate that this is a better solution always? And well, actually, you can do the calculations. You need to know a bit of numbers, because when you go into power added efficiency, you need to know the numbers of gain, right? Because gain goes into the formula in a bit strange way. But you can have the two cases, and from this one is quite straightforward. You have a certain back-off efficiency of the Doherty, and then you can evaluate how things change depending how efficient is your driver and how much gain you have in your driver. For this case, you have to do the calculation. It's a bit more complicated. You have to somehow have an idea what the devices do, but still you can come up with an easy formula. And you can look at the paper if you want a bit more of explanation of what the assumptions are. But overall, what we came out with was basically this graph. We can have a case with no driver, and the PAE is just what it is. And then if we put a driver, we have the case with the single driver in front of everything, case A. And then we say, okay, what if the driver is a gain of 6 dB, 10 dB, 20 dB? And we change the efficiency, and we get these curves. But if you split the driver, the PAE is always better. Doesn't matter what the numbers, what are the numbers that we put in. Now, we did all these calculations, and then after publishing the paper, we start thinking, well, isn't it that, probably I think someone came to us and said, well, that's obvious. Yeah, thank you very much. You could have told us months ago, right? And they say, yeah, of course, because what you do when you put the single driver in front of everything, you're amplifying the signal that you're then splitting, and part of it goes into the auxiliary and is not being amplified. So you're actually spending DC power to amplify a signal that is never amplified later on by the final stage. While if you split the drivers and you use the driver of the auxiliary in class C, it only again turns on then. The other advantage you have is then you end up with a bit more, one more control if you want. I'm assuming you want to have one more DC, but at least in testing you can do that. You say, you actually have one more gate. I can control my turn on of the two stages a bit better. So I can see a compromise maybe between back-off efficiency and linearity. I have two gates that I can use to control that. And then you can use maybe some voltage divider to obtain them in a real circuit. So we came up with this. This was a quite nice thing. We got it published. We were happy with it. So this was a triquint process, was the power amp. They had gallium arsenide, and this design was really targeting point-to-point backhaul at the time. So we got some decent results. The PAE was around 20% in the best case average, back off, which was close to the state of the art. Otherwise, you wouldn't go into the transactions. The only paper that was better was another design from Triquint on the gun. But then when we talked to them, they were a bit saying, yeah, that design, had some oscillation issues. Oh, okay. But you published it, didn't you? So, I don't know. Anyway, talking with Charles Campbell, he admitted that he had some issues. But the raw results were very good, but we never had access to that technology, to the gun, 0.15 they had at the time. So this was a 0.15 gallium arsenide. And the device, quite compact, but you can see we basically split the two devices, and we have a branch line as a 90-degree design. We did some more iterations of this design just to center a bit better. Originally, it was designed to be lower frequency, so we did some iteration. We also combined them in different ways, so we have some more papers around, but the theme is always this. Okay. And then, of course, is the other big elephant in the room, which is the linearity. Okay, so we've seen efficiency, we seem okay. Gain, well, we start having issues, right? Even if we use our method to split the drivers, which turns out to be an obvious one to many people, still you're struggling to get very high efficiencies, let's be honest. But then things get a bit trickier, and we did some. When we started working on these things, we were working at the time with Ericsson, and you do all this effort in designing these complicated Doherty amplifiers, and then you design a Class AB amplifier, and they put them in their system, and once they start linearizing them, you find out you're not getting much advantage. And what is the problem? The problem is linearizing your Doherty is much more difficult, so they have to start backing off the power, and at the end you lose the advantage. So I was trying to understand what was going on. Why is linearizing this Doherty amplifier more difficult? So we started doing a bit of work on these. First approximation, linearity, we can divide it between IM, and IM-PM. In terms of IM, the main contribution is the device itself. Okay, so the different devices, different epi layers, different fabrications, they will respond in different ways. Bias point is extremely important. You can control a lot of the bias point or the behavior by controlling the bias point. Most technologies will show a flat IM where they show a flat IM-PM. So things seems to be going in the right direction there at least. So we choose the right bias, we turn on things properly, we should be okay. IM-PM is a very different beast, and what we work on a lot then was to say, okay, we can adjust IM with bias. Can we adjust IM-PM with bias? The short answer is no. And the reason is the IM-PM seems to be intrinsic in the Doherty behavior. Why? Well, it comes back to Miller effect. Again, it's due to feedback. The input capacitance of a device is due to CGS, but it's also due to CGD multiplied by the voltage gain. What is the voltage gain? Is the GM minus GM times the load. And what we do in the Doherty, we change the load. So inevitably, you have an IM-PM when you do Doherty, if the Doherty works perfectly. Now, you can do strange things like not making the currents perfectly align in phase, and you can adjust a little bit. But if you have the Doherty that works as you should be doing, giving you the good IM and good efficiency, then you have a distortion in phase. What can you do to mitigate that? Well, you can mismatch the input again, but we lose gain, okay? So that's your compromise, really seems to be always ending up there between gain and phase distortion or distortion in general. We actually tried that. This was a UMS design we did, so it's called Imperio. The machines to do pasta. It looks like those machines from the top. Yeah. Anyway, it's just 30 devices. It has nothing to do with pasta. Anyway, you can overlap gain circles and IMPM circles. This is something that was a bit new at the time. And in this device, we have a configurable network. So we could actually match for gain or match for IMPM. And we could actually see the difference experimentally between the two. So you can do things like this and understand, at least now you can make an informed decision on what you're compromising in terms of gain and how much you can achieve in terms of phase distortion. At the time, the target was 10 degrees. And you can see here there was some results there. So if you want to have a look at the paper, are complicated. So it seems to be going down there. Bandwidth, another known problem of Doherty, again highlighted by the fact that we have an higher Q factor. Very recent paper done using the Win MP12 technology. We use combiner that doesn't look like a differential combiner to cancel out almost perfectly the output capacitance. At that point, the design of the Doherty is textbook. You literally have a quarter wave, you have a lambda over 2 for the auxiliary because we cancel out the capacitance thanks to this combiner. Performance was quite good in terms of back-off efficiency getting into near the 30s, which is always a good result for 20 gigahertz. And then very recent, so I didn't do much on the design in these, but I did all the load pool characterization done in collaboration with Polytechnic Torino. This is an ESA project. Published this recently. We tested it up to 3 gigahertz of bandwidth, so 17 to 20 gigahertz, more or less. So we have some good results of MPR up to there. These are results with 100 megahertz of channel bandwidth. So this is really putting together a lot of the things we have learned to improve linearity so that we can actually have good efficiency, but also maintain a decent linearity for a system where probably linearization will never be feasible because it's a type of a pipeline system. So just to close, the message seems to be gain linearity, a big compromise between the two, something to keep an eye on. Maybe adopting some of the things they use in CMOS, at least for the feedback, like neutralization. Not easy to do in 3.5 because we don't have all the metal layers and losses they play a role. But in general, I hope, if you have time to look into this publication, to at least give you some instruments to keep control of all these parameters that you need to compromise. In there, certainly looking forward to your questions, if you have any.
Thank you very much, Roberto. Okay, any questions?
A very quick one. Since you have actually a feedback from output, the input, how did you manage to control the oscillation?
Oh, well, that's another good point. So, of course, behind all these, you have to keep an eye on the stability of the thing, okay? And Doherty, again, because we are trying to get as much as we can out of the other transistors, you just don't want to do in-condition stability because you lose too much gain. So I think, especially in the last design, the big one we used, the N, we were able to access some of the advanced tools, like the STAN tool for stability analysis, because clearly in the Doherty you have the risk of parametric oscillation is very strong, and some of the devices we built, they did have that problem. We did have that problem, yeah. And as usual, then you do the publication and say, I knew it was going to happen there, but it's always the other way. You have the stability, and then you find a way of finding why it was there, but it's a bit too late. So, yeah. So we saw a bit of everything, A lot of it you can solve externally, but some you can't. So we didn't find a way. So, thanks.
Anyone else? Oh, Liam.
So we're actually in touch briefly on the quality of the foundry models in the class C. Now, it's obviously it's a very difficult thing for foundry to produce a logical model that we valid overall because of all bias conditions.
Yeah.
In your experience, how accurate are foundry models?
Yeah, I would say they won't capture perfectly this reduction in things. So what you can never expect is to say, oh, I simulate and I know what the bias point will be, these type of things, because it won't capture. But they will capture the decrease in power, they will capture, and normally they're quite good at capturing where the position of the optimum is. So I think the thing to do is to keep in mind that at the end, you will need to modify that bias point. And having a solution like with two different drivers, that helps a lot. Because if you only have one class C and the bias is off and you base all your simulation on that one being accurate, then it's really problematic. While if you have the two, then there is a lot you can recover by rebalancing the thing. So you're right, you cannot expect them to be, because they are general models and they are broadband and they cover S parameters. So it's just not an expectation. So I think it's also try to, leverage a bit your measurements you do, understand, oh, maybe, okay, I'm losing a bit more power than I expected. I increase the periphery a bit, but then of course capacitance I need to account for, so things like that, yeah.
Okay. That's great. Thank you very much.
Thank you.